Okay, so we have our last talk of the first day. We have Brian Allen giving a talk on the Spacetime Penrose Inequality with suboptimal constant. Whenever you're ready, Brian.
Great. Yeah, thanks. Thanks for the opportunity to speak. And yeah, I'm not gonna this is joint work with Edward Bryden, Demetre Kazaras, and Marcus Khuri. And I'm not gonna assume that you know anything about this setting. So let me start off by introducing the setting for this. So I want to consider the initial data set. So we're gonna have manifold, a Riemannian metric, and a symmetric two tensor K. M is a connected orientable manifold, and G is complete Riemannian, and K a symmetric two tensor. And in general, you can just think of K as some data, but it has some some significance other than that. So it K represents the second fundamental form of an embedding of M3 inside of a four-dimensional spacetime, which is a Lorentzian metric with a time-like vector field orienting it. But for the most part, I won't ever really need this setting, but of course it's satisfying to at least be aware of the fact that everything is being analyzed in terms of this space-time. We're just kind of like simplifying things down. And so this K is actually the second fundamental form of this embedding, but we'll basically hide that throughout the entire talk for the following reason, which is that as long as we assume that the G and the K satisfy certain constraint equations, then we can kind of take Einstein's equations from the four-dimensional spacetime and give an equivalent version on a slice M3, which is what we call the initial data set. So we're going to assume that G and K are smooth and satisfy the following, which is that you want 16 pi mu, which I'll say what is the second is equal to the scalar curvature plus the trace minus the norm squared, and you want 8 pi times J to be equal to the divergence with respect to G of K minus. These are called the constraint equations, and basically if you have a manifold M3 like this with a G and a K that satisfy these constraint equations, then you can evolve forward in time with a nonlinear wave equation given by Einstein's equations and get a space-time. But you can also just analyze everything on M, and that's what we're going to do here in this talk, where this, I said it out loud, but RG is the scalar curvature. U is the energy density. And J, momentum density. Okay, we won't really need the exact form of this equation much, but it is important to note that's how you kind of go from the space-time setting to the connected oriented manifold setting with a symmetric two tensor to talk about initial data sets. And we're always going to assume what's called the dominant energy condition. Which says that mu must be bigger than or equal to the length of J. So J is it's a vector, three-dimensional vector. Okay, so just to keep in mind, in the time symmetric case, so note, so if it's time symmetric, which is just a way of saying for us that K is identically equal to 0, so you have no second form, you have trivial second fundamental form data, then you see that the by that second equation, that J must be identically equal to 0, and you can see that mu is just equal to Rg, and so the dominating energy condition, this implies that the scalar curvature is positive. And so that's, that's why a lot of times you'll see people study these positive mass theorems and things in the case where you just have a Riemannian manifold with non-negative scalar curvature, right? But in general, the dominant energy condition says that this energy density is bigger than the momentum density, the length of the momentum density. Okay, good. So that's our setting. We're going to be working with these initial data sets throughout the rest of the talk. And then we need to say what it means to be asymptotically flat. But here I'm also trying to just make you aware of the setting that we're going to be in, because there's many different ways that one can talk about asymptotically flat. So we'll say that MGK is asymptotically flat. If there exists compact set such that when you remove that compact set, you just get the union of a bunch of different components. So first of all, we're allowing many different ends. So when you remove the compact set, you'll have many different ends, and each end are pairwise disjoint. And diffeomorphic to R3 minus a ball. So what we have in mind in a picture is you're going to have like many different ends, this guy. Possibly 4. And let's say something like this. And you can have some topology in the middle. And so the K that's being removed in this picture would have to be something like this. Whatever is inside here. Okay, and then we'd have 4 ends, and each of these ends needs to be diffeomorphic to a complement. And throughout the rest of the talk, we're going to always start with something like this that has many different ends, but then we'll eventually, after some modifications and things, be always talking about one end at a time, right? But the result will be for any end taken one at a time. And then the next thing you do in any of these kinds of definitions, you have to give a bunch of asymptotic conditions for the end. And so let me just remind you of that part. So if P from the complement of this ball to an end is the diffeomorphism from above with coordinates x, then there's a bunch of asymptotic conditions. I won't write them all down because we're not going to need it too specifically, but just to start writing down here where Q is bigger than half. And this, this O sub 2 just means that you have 2 derivatives with extra decay, with its corresponding decay, where the decay gets better with the derivatives. And you get basically fall off conditions for K and mu and J. And also in this case, we need, maybe I'll just say that we also need this unusual in general, but not surprising when you need to use the Jang equation. So we'll need this extra condition for the Jang equation, which is sort of a well-known need when you want to use the Jang equation. So later on, I'll be more explicit about how we use the Jang equation. That's a big part of the tools that we use. Okay, but the rest of the conditions are quite standard in general. And if anyone wants to know more specifically, I can show you, but we won't need them so much. Okay, but in general, I just wanted to mention that we have, a situation like this where we have many different ends and topology, and we'll look at one end at a time. Okay, so we're in the sort of the most general situation for initial data sets that one would like. And then there's, results by Bartnik and Crucial that say that there is a well-defined energy and momentum defined in this case. So this is by Bartnik. Which says that in this case, there's a well-defined energy taken as the limit over spheres and a well-defined momentum vector. Here, the momentum vector is in terms of the second fundamental form. So you see how you just need to know the G and the K in order to understand the relevant physical quantities on the slice M. And S of R are the coordinate spheres here. Right, because this diffeomorphism to R3 minus a ball gives us sort of coordinates on the end. Okay. So we have all this, the energy and momentum vector, and now we can define the mass in this general setting, which is given by the what's called the Lorentz length of the 4 vector, where you take E as one of the components. There's 3 PIs, which make up 3 more components, and the Lorentz length should give you E squared minus the length of P squared, and that is your mass. This is the ADM mass. Okay, great. So now we have a mass for any one of these initial data sets. And it's an important result that this thing is non-negative in general in this setting with the dominant energy condition holds. And actually rigidity is quite subtle for this, and I'm not going to really talk about it here, but there's lots of results on rigidity for that positive mass theorem in the space-time setting. Okay, so what I want to do though is to introduce the Penrose inequality. So I need to, now I have the mass, which is like one side of the Penrose inequality, and now we need to work on the other side of the Penrose inequality, which involves many more definitions, which are all important to understand the result. So let's switch over to that now. And by the way, just to be clear, this mass is defined for each of the ends, right? So you can have any number of ends that you want. And for each of those ends, you'll get a diffeomorphism to R3 minus a ball, and you can define this E and PI for each of those ends. And again, we're going to take one end at a time. Okay, so now to get the next part, I need to, we're going to do this inequality has something to do with black holes or something, right? So we need to identify like what are the special surfaces that correspond to the apparent horizons or event horizons. And so in this setting, we have to talk about what's called mots and mits. So to start talking about that, we need to consider, sorry, let me get my colors fixed here. Okay, so what I need is let sigma 2 be a closed two-sided hypersurface in M. And we want to look at this thing called theta plus or minus, which is its mean curvature plus or minus the trace on the surface of K. And I need to draw a picture so that we can have some idea what's going on here. So you want to imagine, let's just fix one end and not get into the most general setting for a second. And maybe you have some kind of thing going on like this. So this is your M3. And you want to imagine now for a second that it's sitting inside of L4, though this will only really come up in terms of the second fundamental form. And so then you have a sigma 2, yeah? So and you can think about it as codimension 2 inside of L4 or codimension 1 inside of M. And so there's going to be a normal vector inside of M, and then there's going to be a normal vector inside of L4, right? So inside of M, there's some normal vector, which maybe I'll call nu, and inside of L, there is some normal vector, which in this picture is going to be a little bit funny looking, but something like this. And the point is that H is the mean curvature with imputed with respect to nu, and then you're going to take the trace of K, which is like taking the mean curvature in the direction of M, and you're going to either take the plus or the minus of this. So it's actually like taking the mean curvature in the direction of nu plus or minus N. And we call these, so this nu plus or minus N are called null vectors because in the Lorentzian space, they'll have length 0. And the physical significance is that's the direction which light travels in. Light travels in the direction of these null vectors. And so that's important to us because we can think of theta plus or minus, it's a type of mean curvature. And so physically speaking, if you just shoot off light rays from sigma 2 in every direction, we know every single one of those light rays, sorry, not in every direction, at every point along sigma 2, we shoot off a light ray. That means that light ray has to be moving in the null direction. If we shoot off these light rays from sigma 2 and then track the area of that shell of light, then theta plus or minus is telling us whether that's increasing or decreasing, the area of that shell of light. And since we care about sort of when that area is decreasing, we consider that the light is actually trapped inside of a region. And if it's increasing, then we say that it's untrapped. And this is a way of sort of measuring the gravitational field, whether it's strong or not. When it's negative, we say that the gravitational field is strong, right? So if theta plus or minus is negative, then the idea is that the gravitational field is strong. And we want to sort of figure out where that dividing line is. So we define what's called the marginal outer trap surfaces. So sigma is a MOTS, which stands for marginally outer trap surface, or MITS, which is a marginally inner trap surface. If theta plus is equal to 0 or theta minus is equal to 0. And we call these like future or past parent horizons, and they naturally arise as boundaries of what we call the future and past trapped regions. So basically the regions where these surfaces are trapped in the sense that the theta plus or minus is less or equal to 0, meaning that the light is trapped inside of those regions. Okay, great. So this is going to give us an idea of where the boundaries of these black holes should be. And we need one more definition here to get to the conjecture, the Riemannian, or the Penrose inequality, not the Riemannian one. And so that's going to be the notion of an outermost. So let's see, the last thing I need is we say a collection sigma of disjoint mots and mits is called an outermost apparent horizon with respect to an end. Really, you need to know what end you're talking about, because you need to know what's the outside direction. And the reason, or in the definition, is that if sigma is not enclosed from this perspective of the end by any other disjoint collection. Okay, so if I go back up to the picture I drew before, when I drew asymptotically flat, in some sense, this picture is a little bit boring for this definition, but I'll start here anyway. For each end, I can find a, an outermost mots and mits here. But I want to be careful because for each end, you just pick one of these guys, right? So if I just think about this end, I'll have a corresponding sigma. But in this picture, it's a little bit boring because it's just like one connected component. And that's a completely interesting and reasonable case. It's just in general, there could be like several connected components that you need. So in general, maybe I'll draw another picture down here. It could look, your end could look something more complicated, where like, let's just draw two asymptotically flat ends. And maybe something like this, and then you pick your favorite end, maybe this one, and then you might need, three of these guys. But the point is that when you look outside from these guys now, there will not be any other disjoint collection of mots and mits that separates the green from the infinite end. Okay, good. And in general, it's known that you can always, so this is by Anderson and Metzger in 2009, that if you just look for an outermost mots, there'll be a unique outermost mots. And if you look just for an outermost mits, there'll be a unique outermost mits. But in our case, at some point, we're going to need to mix, and we're going to get an outermost collection of mots and mits, which could be like two mots and one mits. And that's not quite unique because you have to make a choice of like getting rid of certain mots and mits from the unique collection of mots or the unique collection of mits. Anyway, so that's just a little note in general. And then what's the Penrose conjecture, right? So I'm 25 minutes in and I'm just now getting to a conjecture. So let's see. Here's the conjecture. So conjecture. This is called the Penrose inequality. Says that the mass, which I defined earlier as the Lorentz length of the energy minus momentum tensor, is bigger than the square root of this curly A, which I'll say what that is in a second, all over 16 pi, where curly A is the minimum area required to close, and outermost parent horizon. Okay, and so why do I have to define A like this, right? So this is the typical way to define this conjecture. The point is that if you go back up to the picture I've drawn above, you have a particular end in mind, so you have a particular mass in mind, right? I'm just looking at the top end now for a second. And then you pick a parent horizon, with this outermost apparent horizon, which in our case could be a collection of mots and mits, so that there's no mots or mits outside of it. But then you want to talk about the minimum area. And so now there could be a minimal surface sort of outside. I don't know, I'll just draw one here. Like this could be minimal, right? Because the condition, the correct physical condition is that there's no apparent horizons outside, because physically speaking, that's the thing that gives you the boundary of the trapped versus untrapped region and has to do with black holes physically. But then, mathematically, if you're trying to minimize area, the minimal surface is what you want to look at, and there could be one outside, right? You didn't ask it to be outward minimizing, you asked it to have no outward mots or mits. Okay, so then A is really the minimum area. And in general, you notice that although it's possible that the mots or mits could be a minimal surface, it's quite unusual, right? Because you asked this thing to be zero, and so that can only really be zero. The mean curvature could only be zero if you're in a very special situation where the trace k is zero over a surface as well, where you can make the h zero. So that's like not expected in general, as you can tell. Right? Okay, but anyway,
Just
yeah.
ask a quick question. So,
Yeah.
why would we not want to take A to be like the area of the apparent horizon? Like, why do we want to find this minimal surface? Like physically, is there like what is the difference, or is there a difference of what these are measuring, I guess, right? Because I always thought in this, I'll just put it this way. Uh, right, the apparent horizons kind of look at what the black hole is, they find that, right? And then I thought the area of the black hole was supposed to represent, the area of the mass that the black hole has in some sense, right? But now it seems like we're finding. So I guess maybe the question is, how does this A relate back to the black hole? Does that make sense?
Yeah. It's a perfectly reasonable question. I'm not sure if I'm going to give you a very satisfying answer, but I know that there are examples where this is like known to be necessary. Yeah, off the top of my head, I don't know if I have a great physical answer, though I should, because it's a good question. But yes, sorry, I
No,
can't
okay.
give you a
Thank
great
you.
answer off the top of my head. But there are examples I know that where this doesn't work if you use the parent horizon boundary. Yeah, good question. Of course, in the what the next thing I was going to say is that, which is not quite an answer, but is related to what you're saying, is that in the time symmetric case, so if k is equal to zero, then mots and mits are just minimal surfaces. So like this all kind of comes together as one thing. Oops. So when you're in the time symmetric case, you'll hear people talk about the outermost minimal surface and outer minimizing and all that, but that's because these things, wind up boiling down to the same thing, and that's not surprising because of the condition h plus or minus trace k. If k is zero, then you're just asking h to be zero. Okay, good. So in the k equals zero case, so this note's going to continue a little bit. Then we know that Huisken-Illmanen proved this, or I don't know if you know this or not, but Huisken-Illmanen proved this using inverse mean curvature flow for single boundary component, and also recently, I goes in Bonnie. So this is Huisken. fill and use p harmonic functions. And both of these are for so single boundary components, or in the multiple boundary components don't give you quite the optimal answer, but are very interesting. And then Bray, also around 2001, gives arbitrary boundary components using conformal flow. Okay, but in the space-time setting, or where you look at these initial data sets, it's been quite open, and though there's been some special work, so with general K, this has been open for quite some time, and there's been some work by so all this work is under either special assumptions or also with a suboptimal constant. So it's known that this is quite hard. And another thing that's known is, like, there's been several papers written where they basically go through every single method that we could possibly think to use and show why it doesn't quite work, and or show like what you'd have to address to try to make that work. And lots of the methods out there just don't seem to work for whatever reason. And what we're able to show, the theorem that we have, that I'll talk a little bit about the proof in the last however many minutes of the talk. So this is by myself and everyone I listed in the beginning: Edward Bryden, Demetre, Marcus Khuri.
Could I just ask a question before you?
Yeah, of course.
The Bray result is with a suboptimal constant too, or
No, sorry. None of the so in all the results of when k is equal to 0, the constant is optimal.
Is optimal.
Yeah, exactly.
Yeah.
So sorry. So these are all with optimal constants. Yeah.
So it's the general K that becomes suboptimal, or something goes different. So yeah.
Yeah. So with the general K, if you either you have like strong assumptions on, like, maybe it's rotationally symmetric or something, and then you get optimal, or usually you have to make some kind of symmetry assumptions and it's suboptimal. And I forget exactly what every single one of these results are, but that's the flavor of all of them up at this point. And I mean, the flavor of ours is going to be that it's completely general, but you'll see that suboptimal and the constant is actually quite bad. But the strength of it is that it's completely general. There's no assumptions on the initial data set.
And
but
if you were to make the time symmetric assumption, would you get an optimal constant, or no, in your proof?
I mean, I don't think so. No. Yeah. I had to think about that. No, it's not going to work. Yeah, you'll see it. You'll see why. So actually, let me just say that I'm going to state the theorem in the setting I just set up, but we have results for the asymptotically hyperbolic and the asymptotic hyperboloid whole case. And one of those is time symmetric, and it's not optimal. But the reason why we include that is because it's not known in the case that we include. And so it's like asymptotically hyperbolic, but time symmetric. Then we give a Penrose inequality with suboptimal constant. And so that shows you that even in the time symmetric case, we're going to get a suboptimal constant. And the only reason why that's worth mentioning is because you don't get we don't know the Penrose inequality in asymptotically hyperbolic in full generality. But I'm not going to talk about the asymptotically hyperbolic results at all, because then I would have, the whole talk would be introducing definitions. So I've already done way too much time of that. So, but I just want to mention that we have, if you're interested in that asymptotically hyperbolic, then you can go check out what those results look like more specifically. But I've taken so much time to introduce all these definitions, so let me use that to cheat in stating the theorem and just say that the theorem is under these general conditions. Let me not say them again. And then the theorem says the following. So under those conditions that I've already stated above, there exists a constant C, which is less than 10 to the 18th. But of course, we're saying that because it's on the order of 10 to the 18th, such that M is bigger than or equal to the square root of the same A that I defined before over C. And again, I've already defined these things, so let me not write them again. Okay, where again, curly A is the minimal area of any surface outside of the outermost apparent horizon, as I defined for the conjecture. Okay, so again, the C is quite bad, but the strength of the theorem is that it holds in generality. Okay, and anytime I skip writing down hypotheses, if you forget, just stop me and ask me, and I'm going to try to do that to simplify things. And again, so this corresponding theorem has also theorems in the paper for asymptotically hyperboloidal and asymptotically hyperbolic. So you can check those out if you're interested, but I won't talk about them at all in the talk. And now I want to give an indication of the proof, which I'm just going to give an indication of the steps. And so the first step is the first and second step I'm going to kind of wrap into one. So this is the Jang graph. And maybe instead of stating the theorem, well, let me state this proposition actually. So the proposition is the following. So we have MGK as above. And then we're going to associate a Jang triple. We have these curly E ends. And I'm writing too many things down, so let me draw a picture before I move on here to give you the idea. The picture is like the following. So you're going to take one end, as I was talking about earlier, and let's say that end comes with a special sort of parent horizon with, let's say, two components. And so this is going to be your end with some G and some K. And then it's a standard thing to do to take that and represent it as a graph, which is what we're going to call this Jang triple, which is M bar, G bar, X. And that is going to be a graph inside of the larger space, which is going to be like in R cross M with, so this is going to be a graph sort of sitting inside of this larger space, so that when you look at the apparent horizons, now they're going to become, so they're going to become these asymptotically cylindrical ends. So in the statement, you're taking an end MGK is just one of the ends, and you're going to associate it to a Jang triple, which has now many ends because there's going to be the asymptotically flat end, and there's going to be all these asymptotically cylindrical ends, right? And what we need to ensure of this Jang construction is that the second homology of this thing relative to the asymptotically cylindrical ends is 0. And that's something that I won't show you any of the details of, but this is something that was done by Demetre and Marcus and Sven Hirsch in a previous paper. And we just have to go back through that construction and just make sure we can keep track of the area throughout the entire thing. Since in the conjecture, we need to understand the minimal area. So we kind of just go back through their construction that they've already done and show that you can keep track of the area of everything. And the point is, this is a well-known thing that was already used by Shane and Yao, this Jang construction to prove the positive energy theorem, which is that the new, so sigma 0, which is the new asymptotically flat end in the Jang surface, is asymptotically flat. With the right order. And the energy of the end is the same as the energy of the original end. Okay, so you get to do this, you get to take your original end and transfer it to this Jang graph without changing the energy. And what's important is we just have to ensure this second part, which is that the area of any surface separating the asymptotically cylindrical ends from the asymptotically flat end is not less than the boundary of the end that you started with. Okay, good. And so I want to say a little bit more about this Jang graph. This has been done throughout the literature. It's been used many, many times. Again, starting with the work of Shane and Yao to prove the positive energy theorem. When you solve for this Jang graph, again, you're looking to be a graph. MGK is supposed to be a graph inside of this larger manifold R cross M. And so you have a function f, which represents your graph function, and you want it to satisfy this following PDE. Okay, this should, yeah, it's good. And so what is that PDE saying? Well, in general, it's saying that the H minus the trace is equal to 0. I should be saying this with respect to G bar, which is the graph metric, which is just G plus df squared, the usual sort of graph construction. And it's not obvious, but there's like the heuristic reason that when you start with something where H plus or minus trace of K is 0, remember the boundary of this end is such that H plus or minus trace K is equal to 0. When you blow it up, basically what you're looking to do with this graph is to try to place this manifold inside of this larger space so that the induced the K induced tensor is equal to the K that you're given. And when you do that, it turns out that if you have H plus or minus trace K equals 0, then you know that you're going to blow up as a cylinder in order to make that happen. Basically, you're going to force the new and the n that I mentioned before, those two normal vectors, to point in the same direction, and that's going to make it so that you're asymptotically cylindrical on those ends. So this is a well-known thing. Again, it was introduced and used by, or it was introduced by Jang, but then used by Qin and Yao, and then has been, further refined many times by several people, Jan Metzger and Lars Anderson and others. So it's a well-known thing to do. And the importance here is that you don't mess up the area requirement. And basically, this is not too hard to see because of the graph condition will always give you that G bar is bigger than or equal to G very cleanly. So that means you've only really increased areas by doing this. And let's see, what else do I want to say? Now you can embed this inside of a static spacetime. So then oftentimes we look at this spacetime, and now, so the point is that the new Jang triple satisfies it's time symmetric inside of this spacetime. Yeah, so what did you gain? You gained that you're in the time symmetric case now, and you gain that you just need to look at the mass at infinity for this thing. So you've just basically gone from the general initial data case to the time symmetric case. Okay, and I'm using way too much time for all this, so let's see what I can do to sort of wrap this up and make it make some sense here. So we're on this Jang triple now. Everything is just, we're just going to work on this thing where now we just have the mass at infinity, and we have the area of this of some surfaces in between. We're not even keeping track of mots and mits anymore. They've gone to infinity, and we're just going to look at sort of the minimal area of some surface that separates the asymptotically cylindrical regions from infinity. And then what you want to do is use these asymptotically flat harmonic functions that have been used by Marcus and Demetre, and based off of Stern's work, which has become like a whole sort of research direction for many people. So the idea is that if you let M bar, G bar, the Jang is going to, as above, then there exists these harmonic functions on M bar. Which are asymptotically flat coordinates near infinity. So just clear, they're not even coordinates everywhere, but they are asymptotically flat coordinates on the asymptotically flat end, so near infinity. And the gradient of each of these guys will go to 0 on each asymptotically cylindrical end. So this is EL, where so that the energy is bigger than or equal to okay, so this is the main tool that one needs to combine with the Jang graph. And basically what we're doing in this theorem is showing that the asymptotically harmonic functions work on the Jang graph. That's not something that was already done. And actually what's important to point out is that this constant's already not optimal. So non-optimal here, but I just want to make clear that this is where it's non-optimal in a very small way. So I think the optimal constant is supposed to be 1/16 pi. So it's still not optimal, but it's not egregious, right? It's not like 10 to the 18th, like I showed you in the beginning. So this is not where that happens. We just get a slight reduction in the constant that we need here. But basically this says that if you want to bound the energy, then you can try to bound these harmonic functions instead. And I'm going to go over here a little bit, but let me just take a through line to the end of the proof, which is actually not so bad from here. Now that you have these asymptotically harmonic functions on the end, which have certain decay rates on the cylinders and have this mass inequality, then the last thing we need is this inequality by Jang and Sang. So let me finish with that, explaining that, and then I'll wrap things up. So Jang and Sang were studying the stability of the positive mass theorem. And so they were in the time symmetric case. And so for us, though, we're just going to be on the Jang graph. They are not looking at the Jang graph. They don't have asymptotically cylindrical ends. But it turns out that what they established works in that case. We show that. And if I just build this map, whoops, now I need that to be a 1. Where I think of them as coordinates, even though they're not coordinates everywhere, but I still can get a map to R3 using these guys. And then I get another map F, which is where I want to look at where these coordinates are close to flat. So what do I mean by that? I want to look at so if you look at that actually should be G bar the way my notation's been for the Jang graph. If you look at the difference between the G bar on the gradient UI, gradient UJ, like again, if UI, UJ are coordinates, then this really is just a well-defined metric. And you want to look at the difference to the flat metric, and you're going to eventually ask for this to be small, right? So we're going to study for 0. We're going to look at the pre-image of this function. Let me just draw a quick picture here. So maybe you have something like this. And when you take the pre-image of this, you might get something like all this green part outside, right? Because the asymptotically flat end is always close to flat space in some clear sense. And so you know you're always going to contain infinity. And the fact that the gradient of UI goes to 0 in the ends, remember I said that the gradient of UI goes to 0 as you go down the ends. That means that if you choose A and B small enough, you'll never contain the entire asymptotically cylindrical end. And in particular, we know that if, by the way, I'm about to finish, believe it or not, then in this, we're going to pick these things pretty small, but if F is between 0 and 1, then U is a local diffeomorphism. And of course, if you pick A and B small, then you're basically asking G bar to be close in the C0 sense that the metrics are close. So you don't know that it's globally a diffeomorphism, but you at least know that like locally you're close in C0 to the flat metric. Then just to state this theorem that we need to finish off, that there is going to be some level set of F that you can bound this Hessian quantity that I mentioned before. So, and this is some regular level set inside of a range that we're not going to get too much into right now. And so that's the last key, right? Because I said we already have that the energy is bounded below by this Hessian term. And now we have that the Hessian term bounds below the area of a level set. And of course, the last thing we need to know is that the area of that level set is related to the, so this is the Dong and Song result, by the way, so I want to give them credit. We go through this result and just refine it, but it's basically just refining it and noticing that it works in the setting that we are interested in. And the point is that by what we did before, the area of the least, this is sort of bounds from below A, because any level set of F is going to separate the asymptotically cylindrical ends from the asymptotically flat ends. And we said that that area of any surface that separates these things must be bigger than the capital A from the very beginning of the theorem. And so then basically you have what you need, right? Because, so I'm going to be a little sloppy here, but basically now you combine these two things and you get that the energy of this N is bounded below by A, and you rearrange everything and you get the desired inequality, right? That the energy of this N is bigger than or equal to square root of A over C bar. And so it's important here to notice that it's this C that comes from this Dong-Song inequality, which produces sort of the egregious S, what makes it suboptimal on the order of something like 10 to the 18th. It's not so much the little bit that comes from the Jang graph modification. Okay, and then I'll just say that the last part, you notice here I did the energy. This is equal to the energy of the original N that I started with. And that's not what I said we were going to prove. We said that the mass is going to be bigger than equal to this, but that is accomplished by, there's some observation by Eichmeier, Lan Huang, and Dan Lee, and Rick Shane that basically, if you can do the energy inequality, you can perturb it a little bit to get the mass inequality instead. So the last thing is to just kind of perturb. I mean, it turns out you have to be careful and think about it carefully, blah, blah, blah. There's an argument for this, but if you perturb, you can get that the mass is bigger or equal to. You have to perturb to the vacuum case so that the energy and the mass are the same for the perturbed object, and then you can get the result that I started with. Okay, so sorry for going over, but that I will end there.
Okay, yeah. So are there any questions for Brian? So I'll ask one. Did you guys, I guess, is there hope to improve the Dong Song inequality, or does this seem, you know, kind of the best you could do with how the techniques in Dong and Song's paper work to get, that C down a little bit?
Yeah, it's a good question. So we've thought about this and talked about it a little bit. Yeah, so it's really the Dong Song part. I don't think you can fix the Jang part, but again, that part is fairly changes the constant, at least on the order of how much this one does. So there's several steps in the Dong Song argument to like reduce down to results in Euclidean space about capacity and volume estimates and things like that. So one question is like, yeah, are any of those steps, can they be made more optimal, or can you, if you just care about bounding the area by the Hessian, maybe you don't need to go through all those steps and you can simplify that. I think if you go through every single step, I think we made it optimal. So I don't think you can just like go through and be more efficient from what we did, but it's possible that you can notice that like, hey, actually you can just go from Hessian to area this other way, and I don't have an idea for that, but that I think is possible. And yeah, this is where you'd want to try to make some improvement there. Yeah, because this level set of this F, could possibly be quite far out. in the asymptotically flat regime.
Mhm.
But I have
Okay.
no ideas, right? So
Yeah, yeah. No, it's good. It's good. It's good. Thank you.
Yeah.
All right. Does anyone else have maybe one last question before we end the day? Or, let Brian and Hunter start their day.
That's right.
I have a couple of questions if it is not a problem.
Go for it.
One is about U is a local diffeomorphism. You mean that it is C infinity? Since for the Jang equation, I think the regularity is C3 alpha. And so I think that U is also C3 alpha.
Yeah, sure. I mean, we're definitely not going to use anything above C2. Yeah, I mean, I agree with that. We don't need it to be smooth.
C2, I think.
Yeah.
And also I have another question, maybe, I don't know if it is reasonable. After you apply the reduction and the Jang equation, there is no way that you apply, for example, the argument of Bray in order to obtain optimality.
Yeah, I'm not familiar. I've never tried to do that, but as I understand it, like people have tried every combination of the things that are out there to see if it works. And so I don't know exactly why that doesn't work off the top of my head, but I know that people have tried it. Yeah, but I'm sorry, I can't give you like a good reason why it doesn't work. But I think
Okay.
survey paper because yeah, like and it may even be by Marcus and because they've tried all these combinations and pointed out reasons why it doesn't work.
Okay.
Yeah, good question.
Thank you.
Yep.
Okay, let's thank our speaker again, and then we'll
Thanks.
call it a day.